When you click Pay on a website, your request races through a glowing fiber optic cable and bursts into a vast blinking server room. Inside that server's memory, the details of your payment, your name, your shopping cart, your credit card number, live as a complex, multi-dimensional structure built specifically for that computer's processor to use. But to actually process your order, this server needs to send your payment information across a flat network cable to another computer, and it cannot shove that complex three-dimensional memory structure through a one-dimensional wire. It is exactly like trying to drop a fully assembled multi-story Lego castle into a standard mail slot. It won't fit. To actually ship the castle, you have to break it down into individual bricks and lay them flat in a cardboard shipping box. In software, this process is called serialization, or encoding. It takes a complex memory object and flattens it into a long, portable sequence of bytes. When that sequence reaches the destination computer, it does the exact reverse. Through a process called deserialization, or decoding, it unpacks the bytes and rebuilds the three-dimensional structure so it can be read. How efficiently a system handles this packing and unpacking process dictates how fast, cheap, and scalable an entire application can become. There are a few different ways to pack this data. The first is to label everything. Text-based formats, like JSON or XML, spell out exactly what is being shipped in readable words. Look at this JSON payload. It attaches a text label to every piece of information, repeating customer_name for every transaction. While easy for humans, these repetitive labels take massive room, chewing storage space and maxing out bandwidth. To solve this space issue, engineers use a second method, the blueprint approach, utilizing binary schema formats like protocol buffers, thrift, and Avro. Looking at this side-by-side scale comparison, you can see how the blueprint method works. It strips away all those bulky text labels and transmits only the raw data inside a tiny, microscopic cube of binary code. The receiving computer holds a matching blueprint that tells it exactly what each piece of raw data means. By deliberately making the data unreadable to humans, these formats achieve blazing network speeds and drastically reduce storage costs. But relying on shared blueprints creates a new logistical problem. Imagine an engineering team updates their payment system on a Tuesday, adding a brand new field for a discount code. Now, a newly updated server ships a data box containing that discount code to an older server that is still using last week's blueprint. This animated diagram shows how these formats handle that mismatch through a mechanic called schema evolution. When the old server scans the new data array and hits a numbered tag it doesn't recognize, it checks its core rulebook and physically jumps over the unknown bytes to safely read the rest of the data. Because of this byte-skipping mechanic, the old server doesn't panic or crash. The old code and the new code safely coexist on the exact same network. This forward and backward compatibility acts as a safety net. It allows massive tech companies to continuously roll out updates to millions of users without ever taking their systems offline. If we step back from how an individual data box is packed, we can see how these choices shape a complete software ecosystem. On this map of a payments architecture, let's zoom in on the database. Saving information here is essentially shipping data to your future self. It requires strict schemas so that the code you write 5 years from now can still decipher the records you save today. The way data is packed is the universal language that allows distributed computers to talk to each other. By choosing the right formatting method, engineers determine how effectively their teams collaborate, how efficiently their servers scale, and how robustly their software survives decades of inevitable change.